Hello world, I'm Sinue and this is my post-test video about losses, evanescent polarization and unidirectional coupling in guided optical modes. Our starting point will be this slot, mimicking a lossy waveguide where electric field oscillate and with known wave vector Km. In the paper, we demonstrate that the polarization of the evanescence tail and losses are really entangled. To see this, we will use the Poincare sphere, in which, for lossless case, the polarization follows a line from the equator to circular polarized light. While increasing the losses, we obtain a tilting in a non-geodesic cardiac-like path. Any combination of the above is encoded in this poster figure, leading to a polarization-loss locking, in analogy with the spin-momentum phenomenon. This has implication in unidirectional coupling of dipoles in the near field. For a lossless waveguide, emission in only one direction is possible, but when losses are added, the emission is bilateral. Nevertheless, using Fermi-Golden rule and taking into account the losses, we can retune the dipole for obtaining now perfect directionality. The possible combinations are here, where only diagonal terms shows unidirectionality for the electric slab, but it can also implement in plasmonic interface with the SPPs. But this idea can be also obtained using the angular spectrum of a dipole, looking for null amplitude points in yellow because that direction won't be allowed. Here, the spectral landscape without losses is presented. We found that yellow points, 0, lead to unidirectional coupling in the opposite K direction. In the lossy case, we can initially see a clear 0, only local minimum. True 0 values is located above, in the axis corresponding to imaginary part of the K vector, giving rise to complex angular spectrum. Okay. Now we are going to slightly change our topic, but again trying to apply our complex formalities. We are going to deal with the interface between two lossless materials that we already know that it's governed by Snell's law. We are going to place a human-made nanostructure, a metasurface, in between these two materials, trying to obtain and control the phase shape of the transmitted beam. The idea here is that in the left-hand side we have the case without losses, but when we apply losses, the question we arise is, can we control phase and intensity simultaneously? And the answer is affirmative. When we have these defects, we can try to apply a metasurface that it's set up for complex values, and we can see that we have perfect directionality, as we can see in the figure J. The problem here is we need for that an infinite metasurface. And the question is, the model still works when we have a finite metasurface that it's a more reliable model? And the answer is positive. We still have better performance than with the case without any metasurface, and with this passive metasurface we can have an enhancement in the intensity transmitted along lossy materials. Thank you so much for your kind attention.